Hello my dear students, today we'll study about the hashing technique. Some of the portion of the hashing was left out when we were discussing it in the last time in the class. So let us start with the hashing, and hashing is actually a search technique, and you know it well that we have so many searching techniques like linear or the sequential search. The linear or the sequential search was requiring order of n time in the worst case for the searching. The binary search technique that required order of log n time in worst case for searching. We've also seen the index sequential search which required order of log n upon I plus I searching time, where I is actually representing, if we are maintaining an index of every ith element, the size of the index will be n by I. We are performing the binary search on the index, hence it will require log n upon I time, and after this we will get a range of the numbers in which my searching element can be. So that will require I minus 1 searches. So hence the complexity of the search for the index sequential search will be order of log n upon I plus I. Now we have seen some of the tree based searching techniques also. We were performing the binary search with the help of the binary search tree. If our search tree is balanced on both the sides, the complexity will be log n. If the tree is skewed, the complexity will be order of n. It means the best case complexity of the binary search tree will be log n, whereas the worst case complexity, the case in which our tree is skewed either towards the left or towards the right, the complexity will be order of n. We have made a ABES tree. There some corrections were applied on the binary search tree while insertion. If the tree is not balanced while insertion, then we make it balanced with the help of some of the rotations. So complexity of ABES tree for search operations will be order of log n in worst case. We have also seen the B tree and the B plus tree, and the search complexity for the B tree and B plus tree is order of log n to the base t, where t represents the minimum degree. We have studied the B tree with the help of the order m, and if m is the order, it means this is the maximum degree. We can find out the minimum degree by a simple formula, m by 2 seal value. So t is actually the seal value of m by 2. So the search complexity for the B or B plus tree is order of log n to the base t. Now you can see that all of these techniques are performing the search operation in some order of n. It means the search complexity is dependent on input size. If I do not want my search complexity to be dependent on the input size, then I have a technique, hashing. It means hashing is a technique in which how many elements do we have in the table, this actually has no effect on the search complexity. Fine. So what actually the hashing is? Let's say we are interested in finding out a key k. It means that we are interested in searching the key k. We apply some hash function on this key k, and then it gives us a location. It means by applying a simple operation known as the hash function, we can get a location where our element is present. So the search technique that hashing is providing is actually a constant time searching technique. It may happen that in one go you get your element. It means if you apply the hash function on your key, you will get the location. You go to that location and find out if that location contains your desired element. So let us understand about this hash function now. This hash function may be of three types. One is the division method. Suppose I have an array or I have a hash table The size of this hash table is 100. So if the size of the hash table is 100, I will have the locations ranging from 00 to 99. It means the different locations in this hash table, or the indexes of different locations in this hash table, may be 00, 01, 02, 03, 04, and so on and so forth up to 99. That means our hash location is of 2 digits. Our hash location is of 2 digits. So the division method suggests to divide any key by 100 and get the remainder. It means I am performing the modulus with 100. So modulus with 100 will give us the locations ranging from 00 to 99. Let's suppose I have a key 1, 2, 3, 4, 5. So if I take the modulus with 100, this will give us 45. So 45 is the location of this key in the hash table. There is some problem with this division methods. It may so happen that our key is this one, 32545. If I take the modulus with 100, this will again give us 45. If I have another key, let's say 70045, and if we take the modulus with 100, this will also give us 45. It means several key values might have the same location. This actually is a collision, and we do not want the collision to happen. This is happening, or this collision is happening, or the same locations for different key values are coming because 100 had so many factors. It has a factor 2, it has a factor 4, 5, 10, 20, 25 and 50. All these are the factors of 100. Since these are the factors of the 100, so any number which is divisible by 2 or 4 or 5 or 10 or 20 or 25 or 50 may give the same hash location if we take the modulus with 100. So we try to find out a number for the division which has the least factors. We will find out a number that has the least factor, and that actually is a prime number. So if I divide my key value with a prime number, let's say prime number is P, then we will have the least chance of having the collisions. So in this case, where we have 100 different locations, I find out the prime number nearest prime number to 100. We have a limitation that the prime number taken for division may not be more than 100, so we will take on the lower side. It means the number that we select for the division is now 97. So 97 is the nearest prime number to 100. So now we will divide every key with this prime number 97. Fine. So this will give us the locations ranging from 00 to 96. This is giving us the locations from 00 to 96, means the location number 97, 98 and 99 will be not usable. Fine, we can compromise with this much. We can compromise with this much wastage. Fine. So the method is that we will divide the number with the prime number. So this is the first method of the hash function, or this is the first hash function. Now let us understand about this another hash function, which is mid-square method. The mid-square method suggests that whatever is the given key, you find out it's a square. Suppose I have a key 7394. So if you square this, you will get an answer 54671,236. Now if we consider that our hash table is of size 100, that means the hash address is going to be 2 digits. So we have got a 8 digit number, 1 2 3 4 5 6 7 8. So you discard 3 digits from the beginning, you pick these 2 digits, and you discard these 3 digits from the beginning. So from last you have deleted 3 or discarded 3 digits, from beginning you have discarded 3 digits, and you got 71 in the mid, and this actually is the hash location. That means this 7394 is going to be stored at 71 location in the hash table. Or if you are going to search this element, then it is a possibility that the 7394 could be found at the 71 location in the hash table. Suppose I have another key value, that is 2309. So if we do the square of this number, we get 533 1481. So this actually is a 7 digit long. So we were expecting it to be 8 digit long, but it is 7 digit long. So now what we will do, we will discard 3 digits from the last, we will pick the next 2 digit, and we will discard 2 digits from the beginning. So more number of digits are discarded from the right side and less number of digits from the left side. So 31 is the location of this 2309 in the hash table. So this actually is the hash location of 2309 in the hash table. Now another method that we have is the folding method. So folding method suggests, let's say I have this is the key, and I have to find out a 2-digit hash location for this. So what I do, I group these numbers from the last in a pair of 2. This is the first group, second group, third group, fourth group, and fifth group. Now I take the sum of all these, means 15 plus 03 plus 29 plus 15 plus 47. So this is actually 5 3 8 9 17 22 29 6 7 9 and 10, 109. So out of 109, since we require only a 2-digit hash address, so I take only 09 and 1 is discarded. So 09 is the hash location of this key in the hash table. There is a variation of the folding method that suggests, let's say we have 1503 2915 and 47. So this is the key, and what I do, I take the group of the numbers in the pair of 2. So this is first, second, third, fourth and fifth group. Let's say I am keeping the first group as such, but I am reversing the second group. 03, I am making it 30. 29 is same. The fourth group is changing to 51. Fifth group remains changed. It means I have reversed all the even numbered group. Now I get 7 plus 1 8, 9 17, 22, 6 5 11, 2 13, 16 and 17. So out of these two I take only 72 and 1 is discarded. So 72 is the hash location of this key in the hash table. Now this method is the folding method, and this is known as the reverse folding method. The method in which you are reversing every even numbered group while doing the addition. So we are saying that this is the reverse folding method. So these are the 3 methods by which you can find out the hash location. Now you have done enough effort such that the collisions do not happen, but collisions may happen even in these cases. It means our effort has been very much, our effort has not been less for making it confirm that the collisions does not happen, but it happens some of the time. So if the collisions happen, then we have the techniques for the resolution of the collision. So let us understand the collision resolution mechanism. I have already made it clear that the collision means the two key values get the same hash location. Let's say K1 it is also getting the hash location L, and K2 this is also getting the hash location L. So it means there is a collision. Both of these keys cannot be at the same location. We have applied the hash function and we get the location, and the location for both these keys are same. So for resolution of the collision, we have two methods. One is known as the open addressing, and another method is the separate chaining. So open addressing mechanisms is also of the three types. One is the linear probing, and the linear probing method suggests that if H location that we get, that means I have applied the hash function on some key K and I am getting a hash location H. This H location is busy. It means it already has a key. So we cannot store the next key at this location. So look for the hash location H plus 1. If this H plus 1 is also busy, look for the location H plus 2, and so on and so forth. So this is the linear probing method. Another method is quadratic probing. So quadratic probing method is suggesting if H location is busy, go and look for the location H plus 1 square. If this location is also busy, go and look for the location H plus 2 square. If that location is free, store the element or store the key value there, and so on and so forth. We look for the locations like this, whichever location we find it free, we store our element there. Now we have another method in the open addressing. This is known as rehashing or double hashing. So rehashing or double hashing method says if H location is busy, go and find out another H. That means we have found H by some method. Let us find out H dash by some other method. You applied the H function on key value K, you got the location H. Let's apply some H dash function on K and get a H dash address. So since H address was busy, find the location H plus H dash and see if that is free. If that is free, you can store your key there. If not, find out a location H plus 2 H dash and see if that is free. If that is free, store the element there. So we go for the searching in this way. So we have three methods in the open addressing scheme. One is the linear probing, in which I was searching for the location H plus 1 and H plus 2 and so on and so forth if H location was busy. And then in the quadratic probing, since the location H was busy, I have gone for the H plus 1 square location, then H plus 2 square location, and so on and so forth. And rehashing method suggests that compute another hash function, let's say that is H dash, compute another hash location, that is H dash, and find out the address or find out the location H. Since H was busy, go for H plus H dash, see if that is free. If that is not free, go for H plus 2 H dash. If that is free, store the element there. So these are the three methods in the open addressing scheme. Now what is happening in the case of the open addressing scheme, that if I am going to, let's say we are taking the linear probing method, the H location was busy and we have tried to store the element there at the H plus 1 location. If you are storing the element at H plus 1 location, there will be some other element which will have a hash location H plus 1. In future, if that element comes, that will also see the collision. It means This key value is occupying the hash location of some other element. That means when that element will come, the collision will occur. So we have another method known as the separate chaining, in which we suppose the hash table is actually array of linked list. Let's say these are the array of linked list, all are null initially. If this is location 1, let's say 0 location, 1 location, 2, 3, 4, 5, and let's say so on and so forth, 99. So we have array of linked list. If any key value has a hash location 3, I will store the element here. If another element has the same hash location, I will store it next to it in the form of the chain. That means in the form of the linked list, in the form of the linked list nodes. If you have another element, we will store it here. So what is happening in this case, that it is not disturbing the locations of the other values. It is not disturbing the locations in the other hash locations. So separate chaining is sometimes said to be the better method than the open addressing. Now let us understand these techniques with the help of an example. Suppose I have some elements A, B, C, D, E, F, G, H, I and J, and these have the hash locations, let's say 7, 4, 3, 1, 4, 3, 8, 12, 9, 8. And suppose one more element K, which has the hash location 12, and the table size or the hash table size is, let's say, 12, wherein the first location is 1, 2, 3, 4, 5, 6, 7. First location is 7, first location is 1, and the other locations are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Now this, you see what is happening, that we have the key values A, B, C, D, E, F, G, H, I, J, K, and when we have computed through the hash function, the hash locations are coming 7, 4, 3, 1, 4 and 3 respectively. So this is the key value and this is the hash location. So let us understand how we are storing the elements in the hash table. A has a hash location 7, so we will store A at 7 location. This location is free, so we can store it here. So B is a location 4, B will be stored here because this location is free. C has a location 3, so C can be stored here. D has a location 1, so D can be stored here. E has a location 4, but fourth location is busy, so we will try to find out another location next to it. Let's say we are doing the linear probing method. So in the linear probing, if H location is busy, I will go and look for the H plus 1 location. If H plus 1 location is busy, I will look for H plus 2 location. So since 4 location is busy, I cannot store E here, there is a collision. So I do store this E element at the 5th location. Then I have F, which has a location 3, 3 is also busy. So I'll look for 4 location which is also busy. I'll look for the 5th location that is also busy. Then I'll go and look for 6th location, and incidentally the 6th location is free. So F will be stored here. Then I go to see the G, which is having the hash location 8. This is free, so we can store G here. Then if we have H can be stored here. 9, I with 9, I can be stored here. J with 8, you can see that this location is busy, so we cannot store the element here. So we look for H plus 1, that is 9, this is also busy. So you go and see the 10th location, this is free, so you can store J here. And then you see for K with 12, 12th location is busy, so I will go and see H plus 1 location. H plus 1 is 13. We are treating that this hash table is working in the circular manner. So 12 plus 1, 13, modulus 12, I'll come here. This location is busy, I'll to go and see the next location. This is free, so K can be stored here. Now see, if I have to search the element, this was the storage process. The search process will also be the same as that of the storage process. So suppose I'm going to search A. If I'm going to search K, by the hash function I got the location 7, and I see at the 7th location A is present. It means in one comparison I can see that the element A is present at the 7th location, and I can return the location 7 saying that our element has been found, the search has been successful. Then I go for B. The location of B is 4. You can go and see the location 4. Yes, it contains B. So in one comparison only you can find that this B element is present there. Then you go and see the location, this location of C. By the hash function I got 3. So at the 3rd location I see the C element is present. So search is successful. In one go you can find out that the element C is present at 3 location. Now you see D element which has a hash location 1. So you go and see at one location if D is present. Yes, it is. So you require one comparison. Search is successful. For E with 4, no. At the location 4, E is not found. So I'll go and look for 5th location. Since this 5th location contains E, it means in 2 comparison I was able to find E. Now for F, it has a location 3. 3 is busy. 4th location busy. 5th location busy. 6th location, yes, I have a F. So you required 4 comparison in this case. Now for G with 8, you go to 8th location, yes, G is found. So one comparison. H with 12, at 12 location, H is there, so one comparison. I with 9, one comparison. J with 8, J is not present here, so I'll go and see the location number 9. J is not there. I'll go and look for 10th location. Yes, J is there. So I required 1, 2, 3 comparison. Fine. Now I look for K. K has a location 12. At 12th location, we have H. So I've gone to see the first location. No, K is not there. I've gone and see the second location. Yes, K is there. So you require 3 comparison in this case also. 1, 2 and 3. So total number of comparisons that you have done for searching every element in this given data is actually this much. So this is actually 3 plus 3, 6, 7, 8, 9, 13, 15, 16, 17, 18 and 19. If you find out the average number of comparisons required for searching this set of data, so that will be equals to the entire thing divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So this was 19 by 11. We say that this is S lambda. What is S lambda actually? This is average number of probes. Probes means the comparisons. You must have heard about the word probe. That IT department has started probe against some businessman who has declared 13,800 crore rupees income. So probe means investigation. So the average number of investigations that we have done in finding out the data. So average number of probes for successful search. This is 19 by 11. So this is less than 2. Fine, very less than 2. You can say that the complexity is the search complexity of the hashing technique is constant time, order of 1. Now let us compute another another terminology that is known as U lambda. It means this is telling you the average number of probes for unsuccessful search. Meaning of unsuccessful search is that I was looking for an element and that element is not there in the table. Suppose I have a table. And this table has an element, let's say A, B, C, D. Sorry. Let's say this is the table and the elements that we have are like this: A, B, C, D, E, F. And let's say G. So locations are 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this is the hash table and we are looking for the data X at location 1. So data X at location 1 is not present. So linear probing method says that you go and see the two location. So what happens at the two location is blank. The blank means while storage of the data, if I would have observed blank, I would have stored X there itself. Since in this case, after looking X at one location, I have gone to see the location number 2, which is a blank. That means the data X cannot be found. So if the data cannot be found, we say that the search has been unsuccessful. So whenever the condition of the blank is encountered, we can say that the element is not present in the table. So in two comparisons, you have declared that X is not present in the table. One for this and another one for this one. Suppose X has a location 2. So if X has a location 2, the location 2 is a blank one. A blank means X cannot be there in the table. So in one comparison only you have declared that the X is not present in the table. Suppose the hash location is 3 for X. You see that X is not there at 3. So you go and look for the location 4, which is a blank. So in two comparisons you have declared that X is not present here in the table. If X has a location 4, you go and look at the location 4, which is a blank. So in one comparison only you have declared that the X is not present there. Then if the hash location is 5, we go and see the hash location 5. X is not there. You go and look at the location 6. X is not there here itself, here too. So you go and look at the location 7. Location number 7 is a blank one. It means the element cannot be found in the table. So unsuccessful search, and you require 3 comparisons for the same. Then if the hash location is 6 of element X, 6 is busy, go for the 7. 7 is blank. It means in 2 comparisons you have declared that X cannot be found at location 6 or 7, or X is not there in the table at all. If you find the location 7, you see that the location is blank. So in one comparison only you can declare that the element is not there in the table. If the hash location is 8 of element X, this is busy, not having X, then you see F, this is not X. You see at the 10th location, this is also not X. So in the circular way, you go for this location, element is not there. For this is a blank, it means the element is not there in the table. So in 1, 2, 3, 4, 5 comparison, you have declared that the element is not there in the table. Now if the location of the element is 9, 1, 2, 3, 4 comparisons you require. If the location of the element is 10, you require 1, 2, 3 comparison. If you want to find out the average number of probes required for unsuccessful search, then you sum it all and divide it with the total number of hash table places or hash table locations. So this is 2 plus 1, 3, 2, 5, 6, 9, 11, 12, 17, 21, 24 by 10. So 2.4. That means the average number of unsuccessful search is also somewhere in between 2 and 3. So this is also very less number of comparisons, less number of probes. Now This was the method of linear probing. You can similarly understand, do the exercise for the quadratic and the rehashing methods. Let's understand the last topic, that is separate chaining. So for separate chaining, I have considered that we have an array of linked list. So for this question, I suppose that I have 12 linked lists. All are null initially. So the first element is A with 7 locations. So I will store 7 at this one, this location 7. B with 4. C with 3. D with 1. E with 4. So I'll add E here in the fourth linked list after B. F with 3, I'll add here. G with 8. Then H with 12. I with 9. J with 8. And K with 12. Now if I try to find out the average number of probes for the successful search, A can be found at the 7th location in one go. B can be found at the 4th location in one go. Then C can be found at 3rd location at one go, in one go. D can be found at 1 location in one go or one comparison. Then E in location 4, it can be found in 2 comparison, one for this and one for this. Similarly for F, 1, 2 comparison. For G, only 1 comparison. For H, only 1 comparison. For I, only 1 comparison. For J, 1, 2, 2 comparisons. And for K, you require 1, 2, 2 comparison. All these things divided by 11, because we have 11 number of keys. 1, 2, 3, 4, 6, 8, 9, 10, 11 and 15 by 11, which is once again less than 2. So what about the unsuccessful search? Average number of probes for unsuccessful search. Location number 1, in 2 comparison you can declare that the element is not there. Fine. For this, only 1 comparison. For this, 1, 2, 3 comparison. For this 4th location, 1, 2, 3 comparison. Whenever the null encounters, that means the element is not there in the table. So for this, there is null 1 comparison. For this, it is null 1 comparison. For this, 1, 2. For this, 1, 2, 3. For this, 1, 2. For this, only 1 comparison. For this, only 1 comparison. For this, 1, 2, 3 comparison. So total number of places were 10. So I require 3 plus 1, 4, 5, 7, 10, 12, 13, 14, 17, 20, 22 by 10. So average number of comparisons for unsuccessful search is 2.2. So that's all. Thank you.